Yep. So, good morning, everybody. It's really exciting for, as Zidan said, for various reasons, to be here. Just a little bit before I take the helm out from Eli's hands. Eli, I just spent a few days with Eli in another conference in Spain. That's why we were late for this meeting. And I can tell you that he was very smiley, happy. Yeah. Okay, so I'm going to actually a little bit introduce myself and the way I came into this topic through this lecture, so I won't say too much before. But as Idan said, I want to speak about a very complex topic called consciousness. Okay, and I call it the ghost in the machine for reasons that I'll try to expose. But especially I want to lead you through to the notion that we can study this complicated, vague notion of consciousness through scientific means. And so what I'm going to do is first tell you what I mean when I say consciousness, because it's not completely clear. Then I want to convince you that there is a good reason that we should study consciousness. I'll talk a little bit about the mind-body problem and why is it so difficult to study conscious awareness with scientific tools. I'll tell you a little bit about these tools. I'll tell you what are some of the contenders for the instantiation of consciousness in the brain. And finally, I'll tell you about some new implementations of this science into the clinic. Something that is called now disorders of consciousness, and just very recently there were some breakthroughs in this study. So first, what do we mean by conscious awareness? So it's really if I ask you what consciousness is, you'll have a lot of difficulty defining it. And I brought here a quote from the philosopher and psychologist William James, who was great at giving these aphorisms about things. And here he says, when I say every thought is part of a personal consciousness is one of the terms in question. Its meaning we know so long as nobody asked us to define it. But to give an accurate account of it is the most difficult of philosophical tasks. And this task, he says, this is what's important for me, this task we must confront. Okay, we cannot say, okay, it's difficult to define. And it's indeed difficult to define, so I will try to explain it through examples, okay? And I'll start with actually the thing that brought me into neuroscience. So as I told somebody, some of my friends here yesterday at dinner, I accidentally became a neuroscientist. I studied medicine, and I thought I'm going to be an ophthalmologist. My grandmother was an ophthalmologist, and I thought I'm going to go in her path and be an ophthalmologist. But then as part of the duties of a medical student, I came into a stroke rehabilitation department, and I met these patients who suffer from lesions, usually on the right side of the brain, on the right hemisphere. And following this lesion, they develop a syndrome called unilateral neglect. And in a few words, what this means is that these patients, even though they can see and hear and sometimes don't even have any motor disturbances, behave as if half of the world does not exist. So for instance, I put this illustration here because if they have a plate in front of them, they will eat the food on the right side of the plate, but ignore the food on the left side of the plate. If they walk down the corridor in the hospital and the room happens to be on the left side, they will not find the room. But if they turn back and walk the other way in the corridor, suddenly the room is there. These are some examples from patients that I treated back then when I was still practicing medicine. You see this is just a sheet of paper with lines, and you ask the patient to mark all the lines he or she sees on the page, and you can see that the patient misses many of the lines on the left, or when asked to copy these simple figures, this is the production of the patient. The left side is simply missing, okay? Or when asked to simply draw from their imagination a clock face, they draw the circle, but all the details are on the right side of the clock. So this kind of made my jaw drop. I couldn't figure out what it could be that makes these patients ignore half of the world, actually be unconscious of half of the world. And it's even more mind-boggling because of examples like this, where a patient was asked to say whether these two houses are similar, and the patient said yes, they're identical. Even when the patient was asked to move her finger through the contours of the house, she could not say that there is anything different between these two houses because the difference is on the left side of the house. But when Marshall and Halligan, the researchers at the time, asked her to choose which of the two houses she would prefer to live in, she consistently chose this one. Sometimes it was on the top, sometimes it was on the bottom. She consistently chose the one without the flames or smoke coming out of the window. Of course, like our hotel yesterday, last night, right? Exactly. Thanks, Chaim, for this reminder of last night's adventures. I wonder whether somebody was just stayed asleep while it was happening. Anyhow, so this was the first example, but since then there are many other examples. Some of them came from my lab, showing that the patients, even though they deny having any awareness of information on the left side of space, behave as if this information is in their brains. So the information was processed, and even to kind of a categorical way, not only the low-level details of the scene.
Always the left side?
So it's almost always on the left side following right hemisphere damage. It also happens after left hemisphere damage, and then, of course, it affects the right side of space, but usually these cases subside very quickly. So persistent unilateral neglect is almost always after right hemisphere damage, and that's one of the riddles of why. Okay, why this happens? Why is it so lateralized in the brain? But I won't talk too much about neglect here. Sure.
I'm sorry, it's very, very mysterious for all of us. Never heard something like that. I don't understand how you can neglect the left part of something if, for instance, you just turn a little bit your head, then suddenly it's part of the right. How can you miss the flower or the tree? I can't see what it is, but how can you miss that if, for instance, if you would add a second house on the left, would he see it?
That's a fantastic question, and I'm sorry that I'm not giving you a talk about neglect, because if you want later, I can show you. I have many examples on my computer, but the fact is that the deficit is in the awareness of space. Okay, now space, as you noticed, can be defined under different frameworks, right? So it could be the left side of the house. It can be the left side of this whole screen or the left side of your body, okay? And we find manifestations of unilateral neglect in all of these spaces, okay? So just to make the difference between patients who have deficit in half of their visual field, so some patients have deficit damage to the visual cortex, and so they're blind on the contralateral side of space. But if they turn their eyes, now the information falls in the good side, and they see it. This is not these patients. These patients, for instance, when I show you this, they're free to move their head, they're free to move their eyes. It's the left side of space relative to their midline. Okay?
But if they will come from the other direction,
they will miss the other side.
Below, but looking from above, then they will miss the side.
Yes. So I would say that whenever you have a scene, it depends on what you define at that moment as your scene. Is it the house? Is it the whole thing? Whenever you have this scene in your mind, you place it within a space.
You put like a global thing, and then as soon as you have a global, whatever is on the left.
Not only the global, it could be the local. It could be the object. If your attention is now directed to the object, now the object becomes your space, and then the left side of the object will be missed. And I have examples. If you asked the question of what will happen if there would be another house here, and there are fascinating examples of patients, for instance, copying this house, only half of it, and then copying the right side of the next house. So going more to the left, but still neglecting the left side of the house. It's really mind-boggling to understand the behavior of these patients, and you can understand why it drew me into neuroscience.
What is the percentage of patients who have this problem?
That's also a fantastic question, because you might have heard of the book, the man who mistook his wife for a hat, right? Beautiful book by Oliver Sacks. this is a very, very rare condition. I mean, as a neurologist, you see maybe 2 patients like that in your whole career. Okay? Unilateral neglect is a very frequent syndrome. So it affects at least half of the patients who have stroke to the right hemisphere, and probably more. It's just that we're not sensitive enough in diagnosing it at the bedside. So and half of the patients with stroke have stroke in the right hemisphere. So it's like 1/4 of all stroke patients have unilateral neglect. It's a very important clinical entity because patients with unilateral neglect, their rehabilitation time at the hospital is 50% longer, okay? Their chances of being independent afterwards is lower. And my mentor, Nachum Soroka, who was the head of the rehabilitation ward, always says that to treat a patient with unilateral neglect costs as much as a liver transplant. Okay, so it's a major clinical entity in neurology, not rare at all, but completely blows your mind when you think about conscious awareness and the brain. Yes.
Right hemisphere, what part?
Pardon? What part? The most frequent region affected is, as you see in this MRI here, is the temporoparietal junction, right? But you can have neglect following frontal lesions, following basal ganglia lesions. So there's a network of regions which can cause neglect. Somebody? Okay, sorry. I thought you wanted to say something. Okay, so that's more than I meant to say about unilateral neglect.
You'll get 10 minutes more.
We can talk about it later. I mean, I'm staying. So where were we? Here. Okay. So that is the reason that I became interested. I'm still interested in these patients, and every few years after doing a little bit of basic research, I return to the patients to see what we can learn from there. The question that I was trying to understand following meeting these patients is if the patients can actually process this information. The information gets into their eyes, into their visual cortex, into higher level processing. The category is somehow processed. So what is missing to have this additional thing that we call conscious awareness, a conscious experience that we can report and reflect on and reminiscence about later? What is the thing that's missing? Now let's give you some more mundane and less maybe exciting examples of what I mean by conscious awareness. Another example. So you probably have seen this kind of drawing, which you can see either right as a rabbit, if you concentrate on this as the mouth and this is the eye, okay, and these are the ears, and we see a rabbit facing to the right, or we can see it as a duck facing to the left, right? You all see it, right? And the important thing is that it's the same visual input. The same visual input. It's some moments you can see it this way, and in other moments you can see it the other way. I would say that rarely do we see both together. Rarely can we perceive both together. So that's an example of a dissociation between the input and our conscious experience of what we're seeing, or the inference we make out of what's out there in the world. Another example is what we call bistable images. I hope this will you'll be able to see this. So there's a rabbit here. Can you see the rabbit? Okay, so just gaze at it. It's a little bit. This is one of the more difficult examples. I brought it because people know already. So there's a big rabbit here. Let me illustrate it. Okay. 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 Now I will remove. Now I'll remove it. Now, do you still see it? Yeah. Okay. So now there's a rabbit. I didn't change anything in the image, right? But it again shows you that your conscious experience of the world dissociates from the input. Here's another one. What do we see here? Yes. Did you see it? Did you see it before?
What disease do I have if I don't see the rabbit?
Nothing. You're completely fine. You're completely fine. Okay. Okay. So here's the cow. Okay. So the whole point about these examples is to show you that there is something more than the details of the picture. Okay, there's an experience, a subjective conscious experience that you have of the world, and that's the thing that we call consciousness or conscious experience. Okay, I'll give you just one more illustration so that we can go on. It's a nice movie. Please pay attention.
To test just how much attention the attention-stealing design of the new Skoda Fabia actually steals, we left one parked on this ordinary road in West London. We wanted to see if its sharp crystalline shapes, bold lines, and lower, wider profile would attract the desired level of attention. Will the 17-inch black alloy wheels stop passers-by in their tracks? Will the angular headlights attract the attention of other road users? Will a crowd gather to check out its fresh, sporty look? Well, not quite. But did the attention-stealing design distract you from noticing that the entire street has been changing right before your very eyes? Don't believe us? Have another look. Did you spot the van changing to a taxi? How about the scooter changing to a pair of bicycles? Or the lady holding a pig? Let alone the fact that the entire street is now completely different. Didn't think so. So there we have it. Proof that the new Skoda Fabia is truly attention-stealing.
So the people who do the advertising for Skoda stole this idea from a whole field called inattentional blindness. The idea that when we are not attending something, we might actually miss big things that happen in the world. That's another example. So there's something changing every time this picture flickers. There's something which is changing. Can you spot it? Pants, nice. Okay, so you see here the pants are changing from jeans to some other shade. Again, without paying attention, we might miss big chunks of the world. They don't penetrate our conscious experience. Okay, so all these the last examples that I gave you spoke about the content, what it is that I'm aware of at every given moment. We can ask the question about conscious awareness, asking what is the difference between conditions in which you see something versus conditions in which you don't see it, okay, or don't experience it. We can also ask the question about consciousness, about if we look at states of consciousness, and this is maybe the most easy thing to understand about what I mean when I say conscious experience. Think of yourself this morning, just before you woke up, and at the moment that you opened your eyes, okay, and you became, or you even didn't open your eyes, but woke up. Just a moment before, nothing was in your conscious experience, and then the next moment, the whole world is in your conscious experience, right? You experience yourself, you experience the noise from the street, and so on. So this is a very quick transition between different states of consciousness. So some people who study consciousness go in this direction and study the difference between how your brain is like when you're just before you woke up and how it is when you already have conscious experience. Or you can do it the other way. For instance, if people go under anesthesia for surgery, you can look at the transition between being awake and being under the influence of the drug and not being conscious of what's going on around you. So these are different dimensions of conscious awareness. I won't talk too much about self-consciousness, self-monitoring, which is also a very important aspect of conscious experience, but I'll leave this aside for the moment. Okay, so I hope you understand. I kind of illustrated, without defining, I illustrated what I mean when I say we want to study conscious experience, studying what you're experiencing, or do you experience anything at all. So now, why is it an important topic to study? And you know that philosophers have spoke about it, discussed it for many centuries, millennia probably. But is it really an important topic to discuss beyond the intellectual interest in consciousness? So I would say yes. First, there is this psychophysical enigma. Okay, when I say I, people say me and my brain. Okay, what does it mean, me and my brain? Is it not my brain which is me? Okay, and that goes to important philosophical, psychological questions, which I think are worth discussing. There are other more social reasons to discuss consciousness, and that's moral responsibility. Okay? If we know how to define consciousness in a more biological and objective way, then we can ask, when does consciousness arise? And that's important because people believe that moral responsibility comes with consciousness. If you did something unconsciously, right, if you were compelled to do it by some, say, epileptic fit or something, then we won't hold you responsible for what you did. But if you were conscious and if you have intention, then we hold you responsible, right? So moral responsibility is tightly linked to the idea of consciousness. So we can ask, at what time babies become conscious? Are fetuses conscious? That goes to the question of pro-life movements and so on. So it has implications to social decisions. Then come more mundane issues like attentional blindness, which I just demonstrated to you. I call it, why can't I find my phone? Okay, I have actually a big project in my lab looking at it. Not at my phone, I mean at the question. Because it turns out that you move your eyes and we measure eye movements and you look at your phone and you don't see it, you miss it. And then a few minutes later you come to the same place and suddenly it's there, right? Do you have this experience sometimes? Yeah, okay. So the question is, what is the difference between looking at something and seeing it and looking at something and not seeing it? And we're trying to measure brain activity in both these conditions when people search for things. There's the question which is, comes back to the media sometimes, of how much subliminal information really affects us. So you probably all heard about this story of the scientist who has put pictures of Coca-Cola into frames of a movie, and they go so fast that you don't actually notice the Coca-Cola can in the movie, but during intermission, everybody runs to the cafeteria and are suddenly very, very thirsty, and of course they want especially Coca-Cola. So we all heard about this story. It turns out that it's a myth. It never happened. Yes, it was a hoax. Actually, the guy who said he did it eventually admitted that he never ran this experiment. Nevertheless, others have done a lot of experiments about subliminal perception, including myself. And it turns out that in some cases, subliminal information of which you're not aware, does affect your behavior. Okay? And together we did some studies that actually show it using both behavior and brain activity. We can talk about it more later. But of course it's important because we want to know how much people can actually affect our decisions using information that we're not aware of. Okay, so putting them subliminally in our environment. Of course, understanding sleep and anesthesia is a very important clinical entity, which I don't have to talk too much about. And I'm going to just mention the last thing, which I'll get to at the end of my talk, which is acquired disorders of consciousness. So I talked about one, unilateral neglect, which is being unconscious of one half of the world. But there is a more severe case where people are comatose, right, after brain damage or with disease. And then it's really difficult to understand how much they are conscious of, right, because they're not responsive. We know that. They are not responsive to questions or to stimulation. But is it possible that they are actually consciously experiencing? Do they have cognitive processes, thoughts, even verbal thoughts going on in their brains, but we cannot access it? So using tools of neuroscience, this has become a really central line of research in neurology, and I'm going to come to that at the end. Okay? So now the question is, what about neuroscience? What neuroscience contributes to this question of study of consciousness? So one thing is that we can use brain activity to figure out what are the limits of cognition without conscious awareness. So when people are not aware of what they're seeing, using these methods that I just showed you, what we see in the brain about the extent of information processing going on. And we recently surveyed the field about that. And I think more interesting, at least for me, is to understand how consciousness comes about. What is it about consciousness which is different from the other processes, the other cognitive processes that we talk about in cognitive neuroscience? And especially, is there some kind of a secret ingredient, maybe a brain region, a specific neurotransmitter, a specific process in the brain which you need to have so that you can be not only processing the information, but also aware of it. Remember the question I posed about neglect. What is missing? Is this a secret ingredient that if I put it over, like spray it like fairy dust, that I can put in, or maybe to the patient, stimulate a part of their brains and make them conscious again? I can tell you in advance that my research suggests that there is no such secret ingredient. It's a much more complicated state of the brain. So don't hold your breath. I won't tell you about the secret ingredient. Yes.
If I take an aspirin or a drug that takes away my pain, and I'm not conscious of my pain anymore, what area of that will you touch?
So that's a great question. The question is if you take an analgesic, like aspirin, and your pain subsides, what is actually happening, right? The process, the inflammation is still there, right? But you don't have conscious experience of pain. And pain actually is one of the most important fields of research in conscious studies, because it kind of exemplifies so well the distinction between the input and your experience. And so we know about regions in the brain which are especially active when you experience pain. They're in the insula, for example, of the brain. I don't have a picture here, but I can show it later. So we know what regions of the brain get involved when you experience pain. There are a lot of emotional circuits that come in. Specifically about aspirin, it actually does act more on the peripheral side and not so much on the brain. So it acts more on the places where you have the inflammation. Yeah. So I hope I convinced you that it's important to study consciousness for various reasons. Now the question is, how do we do it, considering the fact that there is a gap in our understanding? And I really like this cartoon where you have the neurons and they do whatever they do. You can study and understand exactly the circuits, the connectomics, the modeling, and so on. And then, okay, but how do we jump from this to this feeling of experiencing, which feels so much ephemeral, so much non-physical, right? How do we jump from the physical to the non-physical? Where is this magic, the trick here? Okay, so this is a more like scientific drawing of the same thing from Christoph Koch's book. So there's the outside world, and the information gets into your cortex, and we have neurons, and they spike, and some of those are more sensitive to dogs, and some are not. But okay, but what's next? Okay, how do we get to this to qualitative experience? And so people call this the explanatory gap. I mean, we can imagine how we will study the brain to its minute details, but we cannot fathom at the moment how this thing creates what we feel is as consciousness. Then people see the first part of understanding what's happening in the brain as the easy problem, which is not easy at all. I mean, a lot of careers are spent on this easy problem. And they say that the jump, the gap, is the hard problem, or some people say the hardest problem in science, is understanding this gap. So at the moment, what the field is doing is concentrating on the easy problem. So we first have to solve the easy problem before we can understand what would be the nature of the answer to the hard problem. And the paradigm is trying to find the neural correlate of consciousness, which Francis Crick, the Nobel laureate from the DNA, and Christoph Koch, they defined it as finding the minimal set of neuronal events and mechanisms which are jointly sufficient for a particular specific conscious percept. Okay, let's try to see what are the basic elements which consist or which correlate closely with what it is that we are currently experiencing versus sensing. Okay? So that's what the field in general is trying to do. How do we do it? The basic tool is what I would call the awareness contrast. Okay? So it's actually pretty simple. I've shown you several examples of how you can be aware of something or not aware of something, how you can be generally conscious or asleep, not conscious. And so all we need to do is to measure brain activity when a subject is conscious or conscious of something, measure this brain activity when the person is not aware of this thing or not conscious at all, and compare. The difference between these two would be the neural correlate of consciousness, which is what we're looking for. And it's actually, there are many ways of doing this contrast, different guises, I would say, because not always people realize that that's what we're doing. But first of all, I can study it within subjects, like in all the cases I just showed you, when you're aware or not aware, when you see a rabbit versus when you see a duck, when you see the pants that are changing colors or not seeing the pants. So I can do it, this is within subject. I can do it between sleep and awake. I can do it between subjects. So I can compare, for instance, brain activity in patients who lose consciousness or who lose consciousness to some things and controls, or to the same patients when they are and are not aware of the same things. I can do this contrast between species. So if I believe that a certain species is not consciously aware, if I have reasons to think that this creature does not have conscious awareness, then I can ask what is the difference between the circuitry, the structure of the brain, and the chemicals in the brain, the processes that go on in this brain and that brain, and see what is the difference that could facilitate the evolution of consciousness. Think about humans and machines. AI is becoming very, very strong these days with large language models which mimic understanding, they mimic expression, verbal expression. It's becoming more and more easy to fall for these large language models and believe that they actually do have some kind of a experience or understanding. We all remember from a couple of years ago this engineer in Google who spoke to their, what is it called, Delta? What was the name of the LLM there? There was they were developing a large language model, an AI, and he... Lambda, thanks. The Lambda, and he was speaking to it and got the impression that this Lambda was actually experiencing, and it was very sad about the fact that they were going to delete the code or something, okay? And so it's really easy to fall for this thing, and then we can ask, under the premise that large language models are not conscious, because we know how we program them, there's no reason to think that they are conscious. So if we believe they're not conscious, what is different about the way they work and the way the brain works? Of course, we don't understand exactly how LLMs work, and we don't understand how the brain works, but in principle, that would be a way of going about this question. Okay, there are others. I just want to concentrate a little bit on the first one and show you some of the bag of tricks that we have for manipulating this. I won't speak about all of these because we don't have time. I'll mention just two. Let's start with this seminal example. This is from Stanislas Dehaene. We talked about him yesterday. And so take a look at this image here. There's a fixation point. Please fixate your eyes on this. And I'm going to flash a word, but it's going to be masked by some noise before and after. Okay? Are we all ready? Yeah. Okay, here we go. What was it? No. Okay. It was cat. Okay, cat was there between two garbage noise. And I could let you see it many times, and in some cases it will be good enough for you to see the word, in some cases not. Or I can manipulate a little bit these masks so that in some cases you will see, in some cases you will not see. And then what Stan Dehaene at the time did was measure brain activity when the words were invisible and when the word was visible to the subject. And as you can see, when the word is invisible, even though the subject did not see the word, it still activates a part of the brain which we call the visual word form area. It's a part of the visual cortex which is particularly sensitive to orthographic, to letters. Okay, so this part of the brain gets the information and understands that it is letters that we are seeing, but that's it more or less. When the words are visible, the same region again gets activated, but there's also a wide activation of regions in the parietal lobe over here and the frontal lobe over here. And so the contrast, remember aware versus unaware, the extra activity which goes together with consciousness to Stanislas Dehaene was this frontoparietal network. So they think that this frontoparietal network is the neural correlate of consciousness. And this was done in vision, and the same thing happens if you actually sound the word. You say the word, but it's in the background of some noise, like a train's going on and so on. And sometimes you hear it, and sometimes you don't. And when you don't hear, you don't understand the word, it still activates the auditory cortex, more than just the noise. But if you detect the word, then a large frontoparietal part of the brain lights up, gets activated. So this is a seminal study which has been cited probably thousands of times in the study of consciousness, suggesting that the neural correlate of consciousness, in part at least, is in the frontoparietal activation scheme. I don't want you to take home the idea that this is the answer, okay? Because all of this is still under investigation and controversial, but definitely part of it is this. I want to show you one recent study of us, which, although not completely directly, but it speaks to the same question. So the question was this. So imagine that you see this. Did you see it? Yeah. Okay, we've seen it yesterday, right? We've seen it yesterday. Okay, so usually when you study visual perception, you flash images like this on the screen, much faster even than what I showed you over here. So you show a face, you show the historical museum over there, a house. You compare brain responses to between the two, and you see that this is the response to faces, and this is the response to houses. So, but it's all in the about 250 milliseconds, first 250 milliseconds after image presentation. But if I actually show you this image of the self-portrait of Egon Schiele, if you look at his face, concentrate on the nose, you continue to see it, right? Beyond the initial recognition that it's a face, right? There's still a conscious experience of the face. So we said, okay, if there is this neural correlate of consciousness, something that comes together with consciousness, it has to continue for as long as you experience the face. It can't happen only in the first 250 milliseconds, right? It has to go together with your consciousness. So we did this experiment where we presented, I'll skip this, we presented images of different categories for different durations of time, from 300 milliseconds to a second and a half. And the advantage we had was that we had access to patients who had electrodes implanted directly over their brains. This is done for patients with epilepsy who don't manage with drugs and have numerous epileptic seizures during a day or several a week. And the only way to treat these patients is to find the node, the focus of the epilepsy, and surgically remove it. Okay? So to do that, they first implant electrodes on the patient's brain, have the patient be in the ward for 1 or 2 weeks, wait for seizures, or sometimes evoke seizures, and see where it starts. Okay? And then once you localize where it starts, you can go in the second surgery and remove this part of the brain. So that's an important surgical procedure. We have the opportunity at the time when they are in the ward and just waiting for seizures to happen to run different experiments with these patients who graciously give us their time. And so we presented to these patients the images and measured brain activity. And specifically, you see here all the electrodes that was on the patient's brain. This is Gal Vishne, an LSIC PhD student, brilliant one, who did all this work. And the question is, where over the brain do we see this sustained activity, which will be correlated with your conscious experience, and to see whether this representation remains the same as long as you see this particular image, okay? And we used machine learning, so try what we call decoding, trying to see where we find information about the image. And the result was, to us, very striking and very much opposed to the views of Stanislas Dehaene. We talked about him yesterday during dinner, so I mentioned it specifically. What we see here is that in the high-level visual cortex, which sits here at the bottom, at the base of the brain, we see that we can decode which category the patient is looking at for as long as the patient is seeing it. Okay? As long as the patient is seeing a face, we can tell from the activity in this region that the person is seeing a face and not something else. Okay? And the accuracy is extremely high. Okay? Extremely high because we have very high signal to noise. If you go to the prefrontal cortex, where this theory that I showed you before suggests it is important for conscious awareness, there we see an activity at the beginning when you first see the image, but you can't decode it for the entire duration of the image presence. So that speaks to the importance of different regions for different aspects, at least, of conscious experience. As I already hinted, my view is that there is not one thing that is conscious experience, but different elements that needs to come together so that you consciously experience something. So here we add a little bit to the puzzle. Okay. So I just gave you 2 examples of how we can study this contrast. I'll skip this with your permission, and say that using these various methods of masking things, hiding things, shifting the attention of subject to one place and then presenting things in the other place, different tricks that we play on our subjects, different people get results which are sometimes incompatible. Okay? And that's why I believe the situation is complicated. So some people place, okay, let me go, sorry. So some people suggest that consciousness actually resides, quote unquote, in this specific regions of the cortex which first process the information. So if it's speech, then it's regions. These are the regions which are responsible for conscious experience. If it's faces, then these regions over here will be responsible. Actually, inhibit the hold the conscious experience of the face in these regions. So then we call it sometimes micro consciousnesses. We have a lot of different regions which embody the consciousness. That's one. That's one region. I already showed you I showed you the studies which hint at large-scale frontoparietal network as the most important part in establishing conscious awareness. When you start looking at different regions of the brain and try to see which regions correlate with experiencing or not experiencing something, you find many, many different regions. Not the whole brain, by the way. It's not that the whole brain gets implicated, but many regions of the brain have been implicated in establishing conscious experience. So the situation is complicated. It's not that we don't know anything, and it's not that everything is responsible for everything, but it's step by step putting together the puzzle of what are the different elements that have to come together in kind of a miraculous way, so that on every minute of our life we are actually experiencing something. And the goal of the field, in my view, is to understand all of these elements instead of what some people do is try to fight between the camps. Okay, it's a lot of elements that need to come together. Finally, I want to speak about this revolution in medicine that came out of the field of understanding conscious experience in biological terms. And that's the field of disorders of consciousness. And so you've all heard of patients who suffer from traumatic brain injury or stroke or from degenerative diseases that eventually become comatose. And especially after traumatic brain injury and stroke, the patient may be comatose for a week or 2, but then usually they emerge into a state which has been called vegetative state or persistent vegetative state. And the difference between being in coma and being in a vegetative state is that the patients in a vegetative state have wake-sleep cycles. So their EEG normalizes, like the general EEG pattern normalizes. You have times when the patient is asleep, times when the patient is awake. They may even open their eyes. But otherwise, they're completely unresponsive. So now people have changed the name. Vegetative state was kind of an unfortunate name, okay, for the syndrome. And it's better called unresponsive wakefulness. So the patients are awake, but they're non-responsive, not to questions, not to things said in the room, and so on. And there's a big question that arises how much the patient is actually aware of, because the patient is non-responsive. And sometimes families, sit by their loved one and they hold their hand and they tell the doctors, I told him the story about the grandkid and he shook my hand, or I could see a little bit of a smile. And then they come again and the doctor checks, nothing. Okay, the next day, nothing. And there's unclarity about whether the patient is actually aware of things said and of his own thoughts. So this question of unaware or locked in. So locked in is a name given to a condition which frequently happens. Well, it doesn't frequently happen. When it happens, it's frequently after lesions to the brainstem. Okay, that was at least what you learn from textbooks in medicine. Lesions in the brainstem can actually cut out all the motor commands to the body, and then everything is okay with your cerebrum, with your brain. You can think, you can make decisions, you can even verbalize things, but you cannot output your thoughts or your motor intentions. And it's called locked-in syndrome. And it takes a good neurologist to realize that the patient is locked in. And then sometimes the patient has residual eye blinks, so the patient can actually communicate by eye blinking. You ask a yes/no question, and the patient blinks twice if they want to say yes, or once if they want to say no. And then they go into alternative communication methods like reading out letters, A, B, C, D, and the patient blinks when you get to the right letter, and you can spell out. If anybody has seen the butterfly and the diving bell, it's a fantastic movie. Really conveys the experience of these patients. And the story, the film is actually based on a book that the person with locked-in syndrome wrote with blinks. Okay, whole biography that he wrote with blinks. But these and I had the opportunity when I was still practicing to treat some locked-in patients. And they can do amazing fits as long as you realize the residual motor activity that they still have. But what about those patients who don't have any residual motor activity? How do we know about them? And so now, almost 20 years ago, the first study was published where a 25-year-old patient who was injured in a car accident and was in a persistent vegetative state for several years, when Adrian Owen, now Canadian neuroscientist, has put her in an MRI machine and doing fMRI experiment. And in the experiment, he asked her to either imagine that she was walking around the rooms in her apartment, or to imagine that she was playing tennis. I'm not sure why he chose tennis. Maybe it was because she was a tennis player before. But if you do it in control subject, in healthy subject, you see a specific signature of brain activity which is related to these different imagery tasks. So if you imagine playing tennis, you have this region called SMA activated. If you imagine spatial navigation, it's a different set of regions. And the astonishing thing was that this patient, who was completely unresponsive, was actually activated the same pattern of brain activity that you would expect from somebody who is awake and aware. And that, at the minimum, means that the patient could understand the words and evoke the right cognitive processes that you would expect for somebody with awareness. Okay, so she was following commands. Okay, it's a signature of following command in a patient.
This is someone in a coma?
Pardon?
Coma?
Yeah.
Patient in a vegetative state. So,
Because you mentioned there was two different...
so this is a patient who is in vegetative state, which means she has been comatose, but then she developed a wake-sleep cycle, but otherwise completely unresponsive.
So not even with the blinking of the eye?
No, nothing. But now, following this study, you cannot anymore call her vegetative state, right? Now she has become a locked-in syndrome, a locked-in patient, okay? And since then, several methods have been developed trying to figure out this ability to follow commands in patients who are otherwise unresponsive, or, as I'll show you, to figure out whether patients have brain patterns which are compatible with consciousness. So this is one simple thing. So you tell the patient, imagine moving your right hand, okay? And when you do this for a healthy individual, you get this type of brain activity using EEG now. It's not fMRI, much easier to do on the bedside. You don't have to drag the patient to an MRI machine. So you ask the patient to imagine moving their right hand, and this is the healthy subject, and you don't have to be an expert to realize that you get the same pattern of activity in these 3 patients. Now, these are a minority of patients. Most patients who are considered in unresponsive wakefulness or vegetative state do not show any such activity. But there is a minority of patients who do, and it's really, really important. Here is another one. This comes directly from the study of the neural correlates of consciousness, where people have shown that when you move from a wake state to anesthesia, for example, the complexity of brain activity that you see in the ongoing EEG drops considerably. And here you see applying this to patients in vegetative state. You see that that's a healthy patient. The length of these lines speaks about how far brain regions are supposedly connected. But believe me that the colors here show you some measure of complexity of brain activity. And these are healthy subjects. These are patients who are conscious, patients who are minimally conscious, meaning that they have some signs of overt responses but not stable. Okay? And this is a patient with vegetative state. So now we can take this measure to patients who are supposedly in vegetative state and see where they fall along this continuum to say whether they're actually, we should be called minimally conscious or locked in. I'll show just one more example and then finish with a recent study that was published about that. So that's actually a very neat method. The idea here is that you play to subjects a series of syllables that create words that create sentences, okay? So smart guys fix things, young fans cheer stars, cool bands play songs, deep rock hit gold, okay? And they're presented in a kind of a tempo. Okay, let me play it to you. You'll see what it's like.
Bit thieves, smart guys, fix things, red cat, 8 rats, fast car, hit walls, sweet boys, kiss girls, nice dad, held sons, good minds, save lives, dry fur, rubs skin, great goat.
Yep. Sorry. Okay, so the trick here is that you have syllables coming up at specific frequency. You have words coming up at a slower frequency, right? Because every 2 syllables here create a word. And you have phrases, sentences, which come in an even slower frequency, okay? So you can ask, what does the brain respond to? Will we see only the syllables, which are like physical entities, or will we see also frequencies in the brain which correspond to understanding that these are words and these are sentences? Question? Pardon? The words are monosyllabic, yes. Yeah, right. So it's you're right. It's not words. It's phrases. Smart guys, fix things, and so on. Correct. Thanks for the correction. And in healthy controls, this what you see here is the frequencies. Okay. So 3 hertz is the frequency of the syllables. 1.5 hertz is the frequency of these two syllables, 2 words conjunctions, and this is the frequency of the phrases, of the sentences. And so you can see those 3 peaks in healthy controls, suggesting that they figure out both the syllables and the words and so on. If you and this is the spectrum of the auditory envelope. And now you can ask the question: if you do it in patients, what frequencies will we see? And people have started doing this in patients, showing again that some patients which we think do not understand what we're saying and do not respond, nevertheless show these frequencies which suggest they do actually figure out the phrases. Okay? And this just shows that, I won't go into the details, but it shows that having the signature of sentence understanding predicts your chances from emerging from this vegetative state into a minimally conscious state, and then maybe even into complete consciousness. So they've done it in patients and then followed the patients for several weeks or months, and then you can see that if the patient can actually perceive the sentence, there's a better chance that the patient will eventually emerge into consciousness. And finally, I want to show, I meant this to come after, but never mind. This is a study that was published in the New England Journal of Medicine, which is the most prestigious journal in medicine, just a few weeks ago, where they followed patients with vegetative state for years. I mean, it's a study. They didn't follow them for years. The study was conducted for years over multiple centers, and the result was that they found that 25% of patients who were unresponsive and were considered in vegetative state actually had what they call cognitive motor dissociation, which is what I called before locked-in syndrome. So 25% of the patients that the clinical tests suggested they are completely unresponsive, unaware, actually have some residual awareness. And imagine the impact of that on the treatment of the patient, the prognosis, on what the feelings of the families. It's an immense advancement in neurology. Okay, so to summarize, I hope you all agree with me that having a conscious experience is a critical component of mental life, and the fact that it's an entity, it's something, can be deduced from the fact that it can be disrupted, that you can make this dissociation between sensation and experience, between being conscious, not being conscious. So it can be disrupted, I showed you both in health by these different tricks and in disease. Understanding the neural coils of consciousness will allow better characterization of the different conscious states, which goes beyond what we can do with simple psychological testing. And I showed you at the last part that neuroimaging is already offering better diagnosis for disorders of consciousness. And thank you.
Can you measure or quantify different level of consciousness between species? Say, imagine you argue that some species, animal species, have consciousness. Can you measure different levels like that? And also, can you do it within humans?
So, in principle, yes. In principle, once we figure out what it is in humans that makes a distinction between different levels of consciousness, and we convince ourselves that this is a true measure of consciousness and only consciousness, then we can move this measure to animals. Now, the problem is, the big problem about studying consciousness is what we call the other mind problem. So I am, as William James said in the initial quote, I have intimate relationship with my conscious experience. I know it for sure. I know I'm consciousness. I'm conscious. I don't know it for sure for you. Okay, I believe it because you're very much like me. I can test your consciousness by question, by talking to you, by looking at you, and you give the right responses. So I say, well, if I would have responded this way, you responded this way, it stands to reason that you're also conscious. But then that's it. With animals, the further away they are from the way we are like, okay, the harder it is to say whether they're conscious or not. So what I want to say is that first we have to be very sure within our species that we have the right measure, because there we have at least good belief. Not everybody believes it. I mean, you might be a zombie, a very carefully crafted one, a robot, and humanoid robot. But I have good trust, and so we can, taking this as a premise, I can figure out the measure. But that has to be the first step before I can apply this to other species. This is my stand. I mean, other people might have different views. Yeah.
And for people who cannot blink the eye, can you use the technique of asking them to imagine playing tennis versus this to...
Brilliant. That's brilliant, and it has been done. So the previous paper that was published in the New England Journal of Medicine about these disorders of consciousness was reporting on patients in which they had a yes-no conversation with the patient in the scanner. So nowadays you can actually analyze this brain activations in fMRI, what we call bold activations. You can analyze them online, and they ask the patient, do you live in Bristol? Do you have kids? And if you want to say yes, imagine tennis. If you want to say no, imagine walking around your house. And they got coherent responses from the patient. So in principle, yes, I don't want everybody to go out of this room thinking that all vegetative state patients are like this, or that we can do it with every patient, but you see the prospect of this.
My second question, it seems that all your, or at least a lot of your research is about understanding where is what in the brain, geographically, space. But this is really one dimension. It could be that the communication, same things I have no clue about. Okay, the communication between cells is at 2 volts instead of 5 volts. Or it's this chemical that exchanges instead of that chemical. So there are many other dimensions about what could be consciousness or not.
Yeah, it's absolutely, you're absolutely right. And for lack of time, I didn't go into all of these different ways of measuring. I mentioned regions, but definitely this cannot be the answer. I mean, this is just the geography of what's happening. And a lot of it is being asked about communication between regions. This is one line of research speaking about something called predictive coding, and how predictive coding can actually be related to consciousness. Just in a few words, predictive coding means that our brains are prediction machines. You know that we always try to predict what will be the next thing that will happen, or even to guess what it is that is happening right now. Okay. And the way the brain works is also hierarchical according to this theory. Every brain region predicts what's the lower level brain region will actually say. Okay, so there's a kind of a hierarchical predictions. And according to this theory, the final prediction, your final inference of what's going on in the world after checking that actually this is what is happening is conscious experience. So I'm not trying to defend it or not, but just saying that there are these lines of research. That's another quite controversial theory, saying that trying to mathematically define what it takes to actually create a conscious entity, speaking mostly about integrating information. So you're completely right. It's not only about anatomy, it's also about connectivity. It's also about different processes, different frequencies of brain activity, which might be more or less related to conscious experience. We try to do more than just the anatomy. Yes, very good point. Yes, please.
Will there be any possibility of measuring subconsciousness?
What do you mean by subconsciousness? The question is, can we measure subconsciousness? And I want to ask, what do you mean by subconsciousness?
I don't know if I'm measuring consciousness really yet, but subconscious is something that you can feel that you're not completely conscious of yet.
So I'll try to divide the question into two things that we can call subconscious. Okay, so maybe I have an illustration that will help me. Okay. So take a look at this drawing. Okay, this is the brain. This is the front of the brain. This is the back of the brain. These are regions which are sensory. Okay, where sensory information gets initially processed. Okay, and these are high-level regions, the frontoparietal part of the brain, where more complex global consciousness may be realized. And so this is called, here it says subliminal processing, which could be akin to what you call subconscious. So things that we don't quite perceive yet, but are already simmering in the back of our brains, okay? So for those, yes, for those, neuroimaging is a very good tool, and people have been using it to show that they can actually see this kind of activation in visual cortex even before subjects become completely conscious of what they're seeing. And as I said, there's a review that we wrote a couple of years ago showing all this evidence. So we could measure this with neuroimaging. If you think of subconscious as more like Freudian subconscious, then I don't know. This is very difficult to define, and so I can't give a concrete answer. Yeah, that's just a question.
It seems that you have only measured normal people.
Mm-hmm.
Is that correct?
Well,
Who are normal and who?
yes, but what is not normal?
So you haven't measured any autistic people or any schizophrenic people?
I haven't, but people do study these less in the direction of the neural correlates of consciousness, but more in more specific more specific cognitive domains. Yeah. I don't know if we have time for more questions.
Sorry, yeah, we didn't touch the hard problem, how to connect the hardware to consciousness, and this is of course a very interesting discussion to follow, but we need to make a break.
Give me another hour and I convince you that there is no hard problem.